This video is part of an online course of multivariable calculus, and I'm going to talk about how to set up double integrals in polar coordinates. So let me start. So the goal is this: set up the double integral of f dA over the region R in polar. The first step, graph the region R. Always graph the region R. So just assume that your region R is something like this. Okay, x-axis, y-axis. Just assume that this is, for example, your region R. Okay. Then we're gonna find the bounds of the region R. How to find the bounds? First, given a fixed theta, what is starting and ending value of R? So given a fixed theta, think about what is the starting and ending value of R. Okay, so to do that, graph a line starting at the origin that hits the region R like this. Okay, so I fix theta, and then I see that, for example, this is my first point that hits the region, and it lies on, for example, R1 of theta, and then this is my second point that leaves the region, and it lives on, for example, the curve R2 of theta. So for example, this part of it would be R1, the top part of it would be on R2. So that's how you kind of find the values for R. Just sweep the region by rays from the origin. Think like a radar. Okay, so sweep the region R by rays from the origin. Think like a radar. Okay, and then for theta, find the first and the last ray to hit R. Find the first and then the last ray to hit R. Okay, so for my graph, this would be the first ray. So I'm gonna say that, for example, this angle here would be theta 1, and then this ray in here would be like, for example, theta 2. Okay, that hits the region R. So when I want to set up the bounds, I'm gonna say that it would be the double integral of whatever, and then R is from R1 theta to R equals to R2 theta, and then theta is from the first ray from the positive x-axis actually, which would be theta 1 to theta 2. Okay, pay attention that always write the variables. It would be very helpful, and when you want to use the fundamental theorem of calculus, you don't mix up the variables. And then the inner integral can have the bounds that are functions of theta, but the outer integral should have always numbers at the end. So you cannot have a function of theta or function of R for the outer bounds. Okay, and then after you find the bounds, we're gonna do the third step, which would be replace everything. For example, we're gonna replace x by R cosine theta in the integrand. Then we are gonna replace y by R sine theta in the integrand, and then we're gonna replace dx dy or dy dx by r dr d theta. Okay, so we are gonna use 3 steps to basically set up the integral in polar. So let me do one example. What is the double integral of 1 minus x squared minus y squared dx dy over the region R, which is x squared plus y squared less than 1, x and y are greater than 0. Okay, so I'm given this equation, and I see that I have x squared plus y squared in here, and also I have a disk as my r, so it would be very good that I switch it into polar. So we use usually polar coordinates when the function or even the region is part of a circle, or it's the area between 2 circles, or the disk, something like that, that it's like a circular things. Okay, so the first step to switch it into polar is to graph the region R. So I'm gonna graph the region R, x-axis, y-axis. What do I have? I have x squared plus y squared less than 1. So x squared plus y squared equals to 1. It's a circle of radius 1. Okay, it's a circle of radius 1. And x and y are positive, so we just consider the part of the circle that is on the first quadrant, and then it's a full disk because we have a inequality. So that's the region R in here. Okay, good. Then we need to set up the bounds. So we basically switch into polar. I'm gonna find the bounds. For finding the bounds, first I'm gonna find R. So I graph a ray. The ray starts at here, which is R equals to 0, and it goes onto here. Here is what? Here the last point lies on this curve. What is this curve in polar? This curve is the circle, and in polar, this is r squared equals to 1, so r is plus minus 1, but we care about just r equals to 1 into polar. So this is r equals to 1. So r is between 0 and 1. Okay, and then for theta, I gonna graph the first ray to hit the region, which is theta equals to 0, and then this is the last ray to hit the region here, which would be theta pi over 2. So this is theta from 0 to theta equals to pi over 2. Now I'm gonna replace everything else actually that I have, which is 1 minus x squared minus y squared into polar. This is 1 minus x squared plus y squared, 1 minus r squared, and then dx dy would be r dr d theta into polar. Okay, so I have 1 minus r squared and then r dr d theta. Now let's calculate this integral. So what do I have in here? I have r minus r cubed. So I'm gonna write the outer integral, and I'm gonna take the integral of the inside function, which would be r squared over 2 minus r4 over 3, r to the 4th over 4, r from 0 to r equals to 1. Don't forget d theta. So now theta from 0 to pi over 2. Actually, let me erase this one. So this is what? Plug in 1 over 2 minus 1/4. Plug in 0. It will be 0 d theta. So the answer here would be 1/4. So this is 1/4. The integral of 1/4 d theta would be 1/4 theta from 0 to pi over 2. Plug in pi over 2 and then plug in 0. So this is pi over 8.